So daily quiz is up. All right, one more minute. Hopefully that door won't lock. I don't think it did last time though. Well, it's technically still open anyway. All right. Get your answers in. Because I am locking answers here in 5, afternoon, 4, 3, 2, and 1.
That's my answer.
That's your answer? Why didn't you submit it if you know the answer? How'd you know the question? Do what?
Magic.
Magic? Cool. Well, magic doesn't satisfy it for me. I already got on y'all for doing magic before. How did you know what the question was for the daily quiz?
Oh, I did.
You didn't? You're just guessing 0?
Yeah, together. Don't touch it.
Yeah. All right. Well, I'll tell you this, it's all you're getting is 2 out of 3 because you're still 4 minutes late.
Okay.
You just also got lucky that 0 is the answer for today's daily quiz. So I need to evaluate this and I need to pull up Zoom to continue to share. There we go. Go back full screen. We don't need my faces. So integrate with respect to what first? respect to y first, which means this is integral from -1 to 1 of x times what? So integrate y. Square root of 2 from 0 to x dx. Which means that this is going to be -1 to 1 of x times x squared over 2 minus x times 0 squared over 2. It's actually telling me that that's not, would be 0, yeah. So then, this leaves me just integrating from -1 to 1 of what? Yeah, I'm just going to write it as 1/2 x cubed. So I integrate this with respect to x. What do I get? Eight. I'll be dividing by 4, but since I'm already multiplying by 1/2, that just becomes either multiplication by 1/8 or division by 8. So if I take 1 raised to the 4th power divided by 8, I subtract from -1 to the 4th power divided by 8. Well, -1 to the 4th power is. Which means this is a 1/8 minus 1/8. And gives me 0. Good job, everyone. Any questions for me before we begin today? Yes. Yeah, I had a busy morning than I expected, so I didn't get this long. But all right, so today we want us to talk about integrating in different forms. Would. We'll be able to integrate over the following region. We're going to have a nice little plot, and we'll do not easily, I guess I would draw it. Let's say we get these two curves. Top one is y equals the square root of 2 minus x squared. The bottom one is y is equal to square root of 1 minus x squared. We're trying to integrate inside this entire little band right here that's created. Can I write this as a type 1 or type 2 domain? Yeah, technically I got a type 2. So, Simeon, you said type 2, which means you're fixed between two y values. So 0 less than or equal to y less than or equal to 2 would be your max. And then what else? So you're saying I'm stuck between so if we're running as a type 2, that means we're stuck between these two bounds, and I have to figure out how do my x values change in between those y values. Inside of both those radicals, yes. It's hard. You could set it up this way, but I couldn't do it as a single region. How many regions would I need to split it up in? 2. Because I'd have to be saying, okay, I want to figure out what my changes in x are. Well, I can notice that if I'm anywhere to the left of my x-axis, or y-axis that is, sorry, my lower x values are being created by the outer curve, square root of 2 minus x squared. The inner curve is the square root of 1 minus x squared. And then once I pass that y-axis, that's giving me the lower x values and the upper x values flop. So I could set this up as a type 2 integral, but I couldn't do every single domain. How many domains would I have to do? 2. So then we'd have what? First one, to a, I guess. X would be between 2 minus x squared. Oops. Well, actually, we'd have to change up those functions anyway into functions of y. Ugh, I don't want to do that. At least be all positive y's. It'd be what? 1 minus, I guess for completion, I guess I should do it. X should be equal to square root of 2. Have to square both sides. That's y squared. It'll be 2 minus y squared. And x is equal to square root of 1 minus y squared. And so it was what? Square root 2 minus y squared. Square root of 1 minus y squared. Second region, still between 0 and 2. But now they flip. But notice this region here. What shapes is this actually creating? Semicircles, right? I'm really looking at the area between two semicircles. When we talk about circles, we can talk about an XY coordinate. But how else can we refer to circles? Even if we still want to stay on XY plane, but we can use 2 different variables. If I wanted to figure out, clear out some of this green so I can just get some space to work. That little dot, it has an associated XY coordinate with it. That's not the only way I can look at it as a combination of 2 independent variables. Because it's a relationship to the center, the origin of my XY plane. When I create that vector there, that vector has a specific angle, theta, and a distance from the origin, which is my r. Any point in the XY plane can also be written as a combination of a radius length, or length of your vector, and an angle off of the x-axis centered at the origin. That creates a new type of coordinate system that you should have run across before. You remember what the name of it is? Polar coordinates. So there's this idea that sometimes these domains, even though we can probably stick with type 1 and type 2 and make it work by breaking it up into pieces that are manageable, you know, okay, if I'm gonna have to keep breaking up into 2, 3, 4 different integrals, that's not gonna become a nice thing to do. So maybe I instead say, okay, let's change up the way I'm looking at these functions. Instead of it being functions of x and y, when more appropriate, something like this where we start seeing semicircles, do instead in terms of polar coordinates. And it turns out you can integrate with respect to polar coordinates as well, with respect to r, with respect to theta, because they're still just two independent variables, just like your x and y are independent variables. What was the example I wanted? I thought I had it remembered, or I thought I remembered it. So for that region above, how will we write it instead in polar coordinates? What I'll do is I'll try to copy this real quick. Move it down so we can have the image look at it, and if it might be smaller. Oops, I broke it. Why is it not pasted? Why? All right, screw it. I'll redraw it again. Or actually, I'll do it like this. So how do we define that region in polar coordinates? Is the question. Well, I now have to think about it in terms of radiuses and in terms of angles. So think about the angles that this thing travels on. I start out with both of these curves on what axis? I can say it starts on the x-axis, which corresponds with what angle? 0. And then I just rotate along these curves. The y-axis, which is what? 90 degrees, but we're going to want to stick with radians. What is it in radians? 5/2. And then I continue going on until I get back to the x-axis on the other side, which means I've traveled a total of what radians? What was it? Pi radians. So the angles that I see for any point in this domain is going to range from what to what? 0 to pi. So actually, sorry. All r and theta such that theta is between 0 and pi. And then what about the radiuses? Well, I got to think about, okay, what's the largest radius? What's the largest distance that I get from the origin? And what's the smallest distance that I get from the origin? Well, I get that from looking at the functions themselves. You already told me these two functions are creating what shapes? Semicircles. It's just the upper half of some circle. Which means if I look back at these functions, y is equal to the square root of 1 minus x squared. That means I can turn this into an equation of the circle, and I know from the equation of the circle to quickly determine what the radius is. If you're really familiar with semicircle equations, you could also get what the radius is just from the equation itself. But I square both sides. And I get x squared plus y squared is equal to 1. This is the equation of a circle, centered where? At the origin, because I'm not shifting my x or y coordinates before I square them. What's the radius of the circle going to be? It's going to be 1. Your equation for your circles. X squared plus y squared is equal to r squared. So that y is equal to the square root of 1 minus x squared. That's just the upper half of this equation of a circle, which means it's always going to have radius what? 1. And that was this lower curve, the curve that's closer to my origin. That's always going to be the lower bound of my radius, which means the lower bound of my radius is always going to be what? 1. And I got to think about, okay, what's the upper bound of my radius? Well, it's just this outer curve, the farther curve that's away from my origin. Well, that's again a semicircle. Maybe it's going to help to figure out, okay, what's the equation of this circle? And then from that, get the radius. So we say, all right, well, the equation for the outer line was y is equal to what? Square root of 2 minus x squared. You could have started with the x equals square root of 2 minus y squared as well. You're going to get the same equation in the circle. If I square both sides, move the x squared over. This then tells me that my radius for this circle is actually what? X squared plus y squared is equal to my radius squared. 2 is my radius squared. So r squared is equal to 2. So if I want to figure out what r is, what do I do to both sides? Square root. I need to figure out what value do I need to square to get to. And that is square root. So then my radius are anywhere between 1 and square root of 2. Now look at those bounds for my angles and my radius. Those are just constants. Which means if I translated this to bounds on an integral, the bounds on my integrals are also what? Constants. Whereas we went with this process before, trying to break it up into a type 1, type 2, at least my inner bounds won't be constant. They're functions of y. Which means once I do this integration, plug it in, I might get some weird complicated function. But if I just take this moment and say, hey, maybe if I just transform the problem instead, I actually get a pretty simple domain to integrate across. Now, if I want to integrate across a domain that's in terms of r and theta, then my functions also need to be what? In terms of r and theta. My independent variables need to match up. But here's the great thing. It follows the same rules, because an independent variable is an independent variable. If you integrate with respect to an independent variable, x, y, z, w, q, alpha, beta, whatever, your integration rules are the same. You're just changing up the visual representation of what that independent variable is. So if I want to integrate, let's say r squared with respect to r, what is that going to be? What is the antiderivative of r squared with respect to r? Oops. And then technically I'm going to be the 100% accurate plus my integrating constant because I've got no bounds in integration. Right? But I just apply power rule. What would be the antiderivative of cosine of theta with respect to theta. My integration rules don't change. All I have to do is just change up what my perspective is. And one of the things that happens is when we change up our perspective, it can end up simplifying this integration. Let's just get a quick example integrating with respect to these different variables. So I want us to first do evaluate the integral over region R, which is going to be 3r squared cosine of theta plus 3r squared sine of theta with respect to r first, then with respect to theta over the region r is equal to, set of all polar coordinates such that my radius is bound between 1 and 2. And my angle is bounded between 0 and so doing this integration over this region, I have to identify what the bounds of my integration are, and also which one is the bounds for the inner, and which one are the bounds for the outer. Well, 3r squared cosine of theta, let me write it out, and then I'll ask the question. What am I integrating with respect to first? Which means the bounds for the inner integration need to be from what to what? 1 to 2, what my variable r is bounded by. And I'm integrating last with respect to theta, which means that outer integral is bounded from what to what? 0 to 5. But now I play this same game that we did before. If I'm integrating with respect to r, all of the variables are held what? Constant. That doesn't change. If I integrate with respect to theta, r is held what? But since I'm integrating with respect to r here first, all I need to do is look at the r's. And in fact, I can simplify this down a little bit, because what do both of those two terms inside that integral have in common? 3r squared.
Oh, no.
It's integrals.
Yeah,
Oh, did I? Oh, I put the 3 instead of 2 because I was wanting to pick up that 3. My subconscious slipped through. But they both have a 3r squared in common, which is what I can factor out. That's where 3 was coming from. Being with cosine of theta plus sine of theta, dr d theta. And then one habit I want you all to maybe start doing, you can leave your constant multiples inside the integration, but what can I always do with constant multiples? Take them out front. So that 3 is a constant, and because I'm integrating with respect to r, that cosine plus sine is also constant. So I can pull out both of those factors. So I'll have a 3 times a cosine of theta plus a sine of theta. And I would be multiplying it by the integral from 1 to 2 of r squared with respect to r. And then once I figure out what that is, take it, multiply by this stuff that I pulled out, and then integrate with respect to theta. This trick of seeing these nested integrals might help if I do that instead. So then, what's the antiderivative of r squared? 3. Oops. Sine of theta plus sine of theta. All of that times r cubed over 3 evaluated from 1 to 2. Figure out what all of this is going to look like and integrate with respect to theta. So what do you want to do from here? So I can go ahead and just straight evaluate it. Melbourne, what do you see? Distribute that 3 through, right? Because what am I dividing that r cubed by? 3. Maybe if I had just portrayed a little bit more foresight, I wouldn't have pulled that constant 3 multiple out. Plus it has a 3r squared inside an integrand. And the antiderivative of 3r squared is just going to be r cubed. Same effect that we're going to have right now by distributing that 3 back through, but just some things to be looking out for. Okay, this is cosine of theta plus sine of theta times, now r cubed evaluated from 1 to 2. Let's finally do that. It's going to leave me with a cosine of theta plus sine of theta times what? What is 2 cubed? 8. That's going to subtract 1 cubed. It's going to give you 7. 8 minus 1 is 7. So all I have to integrate is cosine plus sine times 7, and then with respect to theta. Again, what can I do with that constant multiple? Up front, so 7 times integral from 0 to pi of cosine of theta plus sine of theta with respect to theta. And kind of like what we saw when we were integrating all those type 1, type 2 domains, once you're done integrating with respect to one variable, it should disappear. It should only be left with a function of the other variables. It's kind of your check to make sure that you're doing this correctly. All right, but this is a nice little simple addition. I can figure out the antiderivative of both of those two parts are. What is the antiderivative of cosine? And what's the antiderivative of sine? Cosine evaluated from 0 to pi. And now the calculus is done, just some evaluation. So we're going to have 7 times sine of pi minus cosine of pi minus sine of 0 minus cosine of 0. What is sine of pi? 0. It's on the opposite side of the x-axis. Sine corresponds to which coordinate? The y-coordinate. So if I'm on the x-axis, I know I've got no height. What about cosine of pi? Negative. Farthest left on that unit circle, x-coordinates is -1. Then I'll then be subtracting sine of 0, which is 0, minus cosine of 0, which is. So I play around with these. I'll do 2 inside, because I'll have a negative -1 turns into a +1, and second negative -1 turns into another +1. Inside those square brackets, I get a 2. 2 times 7 gives me the 14. So, as long as I can get to an integration, even if it's in polar coordinates with r and theta, does the process really change up at all? No. What do you think the harder part is? Setting it up. Yeah, go for it. Mhm.
If you run X,
No, because that'd be creating, what does that create? I don't know what shape it creates off the top of my head, but it wouldn't be a circle.
if both have a negative now from somebody else.
So when you say both have a negative, you mean like negative,
X squared minus Y squared.
equals r squared? Yeah, that wouldn't create real value. That would be a complex value function. Or technically a complex valued implicit function. Because there's not going to be any x or y values except for 0. They'll be able to give you r squared value, and that's only if r is 0. The only solution to that equation would be x0, y0, and y0. It wouldn't create a shape of two functions at all, or any image. All right, so then, question is, how do we convert two polar coordinates? Specifically, if I have a function of x and y, how do I turn this into a function of r and theta? Well, our relationship comes from those right triangles that we build on that Cartesian coordinate system. So remember, this is coming from being the outer edge of some circle. So a circle always has a radius r, which becomes the hypotenuse for that. We know that we get some x and y coordinate on the edge of that circle. And that's giving us that relationship. If it's centered at the origin, x squared plus y squared is equal to r squared, because that's coming from what theorem? Equation of circles coming from what theorem? The Pythagorean theorem. That right triangle, because that horizontal line is the distance you're traveling in the x direction, vertical line your y direction. But then we said, okay, based off of coming from the x-axis, we get an angle theta. And then we defined my sine and cosine function. Now, this is not a unit circle. If it was a unit circle, I'd let r be 1. You'll see that you're going to come out to the same answers as how we defined sine and cosine originally. But to define the sine of theta, I take what sine divided by what sine? Opposite over hypotenuse, which in this case is labeled what? Cosine is what over what? X over r. That gives me two relationships that are able to allow me to transfer between the x variable, a theta variable, and an r variable. But I want to figure out, okay, if I want to take x and y, what should they then look like in terms of r and theta? Well, if I take both of those equations and multiply them by r, that's going to then give me x is equal to r times cosine of theta, and y is equal to r times what?
So,
Sine of theta. So that right there is the relationship that we're just going to have to take advantage of. If you give me a function of x and y, turn it into polar coordinates, I just replace my x's with what? And I replace my y's with That'd be your functioning polar coordinates, yes. Now there's one other thing that we have to be careful. And it's going to come into a nice little result, but we're going to have to do a little bit of work to get there. Is it actually 141? This clock is sometimes never right. No, it's usually set to 941, I guess. So yeah, we're good. So I should have enough time to explain this. Oh, instead of our sign. Yep. So overall, what this is giving us is that if I'm integrating over a region with xy coordinates for a function f of x comma y, with respect to the area of the rectangles that you're creating in a rectangular region, this is going to be the same thing as if I change up my region to be in terms of polar coordinates. Look at the function as a function of r cosine of theta and r sine of theta. But there's something important that we have to resolve. Is what this dA is, the change in the areas of one creating. So for rectangular regions, and then anything that at least we could bound as a type 1 and type 2, so we at least had two fixed vertical values. We were taking our domain and breaking up into very small ones, squares. Technically rectangles, but square is a rectangle, right? So then each of these little rectangles that we're creating to get a rectangular prism, to get a small approximation to the volume over that area, and then we add them all together. We take it in limit to get our actual integration. Well, that told me that for a rectangular region, my change in my area was just, okay, change in y or and times change in x, or change in x times change in y. It didn't really matter. But now I have to think about, I'm in polar coordinates. I'm no longer talking about a rectangular region where it's set length in x and set length in y. I'm now working with polar rectangles, which means I'm set a distance between, or sorry, let me draw it and then explain that. Polar rectangles actually have a curve to them. We're putting them on an XY plane. Because rectangles, we think as a fixed value in one variable and a fixed value in the other variable, right? Fixed x value, fixed y value. And now I'm dealing in polar coordinates, which means I have to have a fixed r value and a fixed theta value. So I get my two theta values really here, theta 1, theta 2, and then I have two radiuses, R1 and R2. Just let me draw them all in dotted lines for blue element. So I want to figure out how to calculate the area of this region in between these two radiuses. Well, I can't go to my normal, length times width. It's my area because there's curvature. But this is coming from circular coordinates, which means this is part of a circle. So I can find the area of a circle, of a sector of a circle. To get the area of any sector of a circle, it's just 1/2 times the angle that I will travel inside the circle times that radius squared. Because if you think about it, to get the area of a circle, it's 1/2 what square? Or it's actually not 1/2. How do you get the area? What was the equation for area of a circle? Pi r squared. And this is coming from 1/2 times traveling 2 pi radians around an entire circle times r squared. So then to get this region in between those two, all those red lines, well, I have to just think of it as areas of sectors of a circle, one circle coming from the inner, and then one circle coming from the outer. So if I just take this larger piece of a sector and then subtract that smaller piece, I'm going to get that area of the region that I'm looking for. Well, this area right here, 1/2 times the angle that I travel, which is just the difference of those two angles that I have, times the outer radius, R2. That inner sector of area is 1/2 the difference in my angles to figure out how far I've traveled in total, go from one edge of this region to the other, times R1. Quantity squared. Meaning that, hey, what do these both have in common? Well, 1/2 theta 1, theta 2 minus theta 1. Then I subtract it by R2 squared minus R1 squared. Well, that's a difference of squares. I can factor that. And when I do that, it's going to factor into an R2 plus R1 and R2 minus R1. Well, the difference in those angles theta, I can represent as my change in my angle. Because our goal in Riemann sums is to make these rectangular regions small, whether it be in rectangular coordinates or polar coordinates. I'm going to have this R2 plus R1, but then that difference, R2 minus R1, is just a change in what variable? A change in R. How much those two radii or radiuses differ from each other. Radii, I think it's technically the grammatically correct term. So that means I sum this all up into R2 plus R1 all over 2. That's my change in theta. That's my change in R. That's giving me the change in area for that polar region. But then I have to think about, okay, I'm setting a Riemann integral. We keep breaking up all of these polar coordinate rectangles into smaller and smaller pieces. And we still do the same calculation, right? Figure out your area, multiply it by your height. So you have a particular point in the region and a particular angle, radius angle. And then you're multiplying it by the change in the area. So you get your height in the base area, that's going to give you your volume. But we just said that change in the area is defined as R2 plus R1 divided by 2, really kind of the average of these two radiuses, the midpoint between them. Times your change in theta and your change in r. Now think about it. We're going towards infinity, which means these pieces are getting smaller and smaller and smaller, which means those two radiuses, R1 and R2, are getting closer and closer to what? Not to zero, together. They're getting closer and closer to the same value. If I take that limit, R1 and R2 are going to become the same value. It's going to become whatever the radius is, whatever some value R is. So if I take R plus R and then divide it by 2, I really just get what? Yeah, get the radius R. So it turns out that weird term that gets created really just means that I'm going to be creating a variable that I multiply. So if I'm ever integrating over a polar coordinate region, and I'm integrating with respect to this Riemann sum. So I'm taking these Riemann polar trapezoids, so to speak, polar rectangles, and the rectangular prisms, letting them go to infinity, adding them all together. Even though it doesn't necessarily matter which order I do first, whether I integrate with respect to R or integrate with respect to theta, really how I integrate over that region is R times dr d theta. So for some of you who've gone through the homework, you probably always see kind of this little R show up right before the two integrations. That's where this is coming from. Because if I ever want to integrate over polar coordinate regions, I have to make sure I take whatever my function is and take it with R times dr d theta. So overall, this is the last thing, because I definitely see the time. My rectangular region, if this is a function of x and y, it doesn't really matter. dx, dy, dy, dx, we're good. I can end up changing this into an integration over a polar coordinates region. But then I need to make sure that I change that function to be in terms of the polar coordinates based off the relationships we found between x and y. And then multiply it by an r. And then integrate with respect to r and with respect to theta. So on Wednesday, we're going to be doing this, putting this into action. Okay. So you've already attempted to tackle this last one. If you just did a blind transformation with x and y in this case, and didn't multiply by the r, you have been getting your answer wrong. And this is why. Okay. So I'll turn it so you can try to get more in there. But if you have questions for me, go ahead and ask. Otherwise, use your little break before DPQ. You know if they're able to get into 305, Melbourne?
Yeah.
Okay.